Usual atom due to electron spin, and also due to the orbital motion of electrons. Individual atom will behave like a dipole, and some will have dipole moment, the net dipole moment of that given atom. What is the net dipole moment of that will be 0. So what is the induced magnetic field here? 0, and there is no external magnetic field. When a same substance, when I go and keep this in external magnetic field, so what will happen to the dipole moment of individual atoms? They'll get aligned. And what is that BM? BM will be like this. And the external magnetic field is, I'll show by dotted line. This will be the direction of external magnetic field. And there'll be a small magnetism will be induced. So who will contribute this BM? The orbital electrons as well as the electron spin. I'll give some small rough diagram. Even the spin also will contribute the magnetism here. Both things. So who is responsible for this BM? Both the spin of electron as well as also the angular velocity of the electron. So call this omega 1 and another is omega 2. Both these angular spins are responsible for, both these angular velocities are responsible for this BM. So the induced magnetic field, the first point I'll write, the induced magnetic field is due to orbital motion and spin of electrons. Everything that both are in diameter only due to orbital motion. Here both the spin as well as the speed will change. Because of that, what happen? A net dipole moment will come, and the magnet dipole moment of individual magnet, what happen? Individual atom slowly will get aligned and will get a net EMF will be, a net magnet will be induced, and that will be in the direction of B naught. And if I go and check it now, this BM will be BM in the direction of B naught, and the value of BM will be less than B naught. And because of that, what I can put, susceptibility will be positive and very small. And what about mu r? Will be positive and will be greater than 1. Mu r will be, because what is mu r? If chi is positive, what happen? It will be greater than 1. And they'll be attracted by the magnetic fields. They are attracted by bar magnets. So there's a overall, like you can say, particular thing. So now when I go for, as I increase the temperature, what will happen to paramagnetic substance? Any effect on the magnetization? So when we vary the temperature, so any relation, anything will happen to the intensity of magnetization. Anybody? We know some small idea, no? If you vary the temperature, anything will happen. Anything will happen to the atoms. I think a little bit chemistry, that's why I'm asking. If you vary temperature, anything will happen to the substance. Okay, let's directly ask, let me happen to substance. You go back to conductors. So as you vary temperature, so what will happen to the atoms? They'll start vibrating, no? So due to that vibration, what will happen? The slowly the water that magnetism there, it start decreasing. It start decreasing here. So if I go for a graph, so the magnetization. So shall I say intensity of magnetization, and there's a temperature, or say susceptibility, better you call. This will be, the curve will be like this. What is this susceptibility? What is this susceptibility again? Decreases. Okay, fine, that one. Susceptibility, again go back. Susceptibility, what we define? It's a measure of, it's the ability of substance. It's a measure of the nature of magnetization. So what happened that the overall magnetism start decreasing, means as you increase the temperature, the BM will decrease. Why BM will decrease? Because the atom starts vibrating. Due to that vibration, the spin as well as particular orientation of that, means now they'll get oriented. Because of that, the arrow will make them slightly like this. So what happened to net dipole moment? Will decreases. Net dipole moment will decrease. Intensity of magnetization decreases. If intensity of magnetization decreases, I think we have defined one quantity. H is something which is external, no? Inside the solenoid, it depends on solenoid. So definitely what happens, as the net dipole moment decreases, as the net dipole moment decreases, I will decrease. Phi decreases, chi will decrease. So therefore, I'm putting this one here. So this is some sort of like a rectangular hyperbola where the relationship is given by this one. This C is called as Curie temperature. Very important. You get plenty of numericals based on this data. Now, what is the overall idea? As temperature increases, let me put in a systematic order. Temperature increases, then the net dipole moment decreases, intensity of magnetization decreases, susceptibility decreases. Any reason for that? Susceptibility equal to I into H. And what is the intensity of magnetization? Total dipole moment per unit volume. V is not voltage, volume, total volume of a substance. I think all are interrelated. And what is this M? M depends on what? Number of atoms into dipole moment of each atom. What is M? M, what you can write? Number of atoms or dipoles into dipole moment of each atom. I think in numericals, you are supposed to think in this way. You can ask questions of why you are not writing, and it's a constant. Curie temperature. So what is the value of C? For different materials, the value of C will be different. There's one more big headache what we are having. C is not some sort of like a constant, like a speed of light, that one. For different materials, it will be different. That's what he's saying. For different materials, the value will be different here. Again, the Curie, what pen Curie constant, Curie temperature, it's called a constant. For a given material, it will be constant, and for different materials, it will be different here. So that's why what pen in books, what pen nobody will go for the value of C, because it's a very difficult quantity to measure. We don't have much data. I think if you refer some very good research materials, you'll get that one. But ordinary books, what happen? Nobody is able to publish the value of C even for any substance also. Very rare we have seen. I have collected few. I'll just show that for different materials, what is the value of C. For different materials, the value of Curie temperature will be different. It is not a speed of light. Curie temperature. So now what will happen to this paramagnetism? As you increase temperature, slowly it will decrease its magnetism. The induced magnetic field will decrease here. That's what he mean to say. Okay, now we'll go for the last one, the ferromagnetism. This totally now ferromagnetism. So only after quantum mechanics came little bit idea, they were able to explain. Prior to that, no exact idea. Or ferromagnetic material. Now, if you take the iron, is it a magnet? Iron is not a magnet. No? You take that natural iron rod. Is it a magnet? Nothing. Can I make it a magnet? It's how it is possible? What we do? How do we make a magnet? There are artificial magnets, are there? No. What is our main purpose? Our main topic is what? I have to produce a very powerful magnet, small size, but it should have very good magnetic field. That was our main target here. Then I checked it, several materials, nobody is satisfied. Then I'll come for the metals. What are the metals like iron, copper, steel, copper, nickel, cobalt. Then what happened? I can what happened? Make a powerful magnet using these materials. Sir, how it is possible? Okay, let's do one thing. Let's go back to some 1,000 years back or 500 years back. I think 500 years back there was no electricity. Am I right? Then how they were able to produce magnet? Sir, naturally available. No, they were able to produce even what? Powerful artificial magnets. How they were able to produce? Just very simple. Take iron block. You start hammering it. So hammering means take hammer. This one. Start hammering it. There's